Okay, everyone. So welcome to the Pulse seminar. I'm delighted to introduce John Bell. John Bell is quite well known in the community for bringing a combination of systems and programming languages and software engineering mentality to problems and finding really innovative, performant solutions to problems that we haven't been able to solve before. So today he's going to be talking about how you can find out what parts of your software depend on what other parts, especially when you didn't want that in the first place.
Thanks so much, Mike. So good afternoon. Let's just get started. So speaking of a room of computer scientists, and especially a room of computer scientists and PL and software engineering, I don't think that I need to convince you that we need to make it easier to make reliable software. So just to kind of motivate my research, what are developers in the field doing in large shops, small shops to make reliable software? So there's a lot that varies, but at the end of the day, we're testing. We can talk about ways to make new tests or ways to make better tests, but at the end of the day, everyone is making tests and they're running these tests. So how can we help them? How can we make this easier? So my work, especially what I'm going to discuss in this talk today, focuses on making it easier for developers to make reliable software by making testing easier. Specifically, I'll describe several techniques to make it easier and cheaper to execute tests, and several techniques to make it easier to specify complex tests. Also mention that this talk focuses almost exclusively on work that I've done in Java. A lot of this stuff is applicable in other languages, and I've considered more broader applications for things too, but today we're going to be talking about Java stuff. So again, brief background, most of my work is in software engineering. It often ends up, as Mike mentioned, overlapping with software systems and program analysis. But today I'm going to focus on two works that make testing cheaper, VMVM and ElectricTest, and two works that make overall reliability easier, Pebbles and Phosphor. So one common thread between all of these works, aside from their connection to software testing and reliability, is that their insights are all related to various forms of program dependencies. So through my various projects, I've made tools to automatically detect dependencies between different software components and at different granularities. For instance, we might consider dependencies between individual variables or between high-level components, which may not be special in and of themselves, but by specifically finding dependencies that may be hidden or unknown to developers, like in this example here, where calling one function might have some unintended side effects on some other variable somewhere else, maybe we can discover and build approaches and tools to help developers ensure that their software is reliable. So the first set of projects I'm going to describe focus on making software testing faster, and were published at ICSI in 2014 and FSC in 2015. And these projects leverage insights and dependencies between test cases. So let's start off by taking a step back and looking at the role of testing in a typical simplified software development lifecycle. We start off with some developer who creates or changes some code. Then they want to see if their change was successful or not, so before doing anything else, they build and test it. And then if this looked OK, then they're going to commit this to some version control, and then go back, find the next problem they have to solve, try and solve it, build, test, and repeat. And our question is, how long is too long for developers to wait in the step in the middle where they're running a build, and they're running their tests, and they're deciding if their change might have been successful? So I have reports from some of my industry partners of these builds taking days, and that's clearly too long. Others report builds taking several hours. These long builds would pose a serious problem for any development methodology. Even if we're only doing this phase nightly, it can still become tough to keep up with. Even in cases where builds are taking, say, 10 minutes, this latency can still be significant for developers in a continuous integration environment. Yes?
So just to be clear, is this just the build process, or is this also build and running all the regression tests?
I'm saying build and run all of the tests.
Got it.
So where we're going to is, what does that process really entail, and what can we do to speed that up? So we kind of have this hypothesis that testing is dominating that time, but does it? So to study this impact of testing on these long builds, I studied the 351 largest Java projects that I could get off of GitHub using Maven, finding that across all of those projects, testing took on average about 41% of the total time to run the package step, the build of the Maven project. If we zoom down, excluded the really short ones, the ones that were completing in less than 10 minutes, testing definitely took the majority of build time, on average about 60%. And then if we zoomed in and really look at the projects that were the very slowest, where it took an hour or more to build, those that might benefit the most from some form of acceleration of this whole process, we found that testing was taking on average about 90% of the build time. So the takeaway, if we can accelerate tests, then we can accelerate this overall process of the build. So what we're trying to achieve is maybe an order of magnitude reduction in testing time. We want to take those nightly test suites and be able to run them over lunch. We want to take our current lunch suites and run them maybe over just getting a coffee. We want to take the ones that took a coffee and maybe just run them while we're checking our email or checking Facebook quick. So what's the problem? Test acceleration is something that's been studied in literature and industry. What are typical techniques that have been proposed in literature and practice, and where does the dependency issue come in? So for instance, one technique is test suite minimization, where we automatically examine some test suite to identify redundant tests using some measure of redundancy, and then remove tests that we find to be redundant. We have less tests to run and it goes faster. Or we might consider regression test selection. We're given a specific change set for some regression test suite between the last time we ran it and this time. Maybe we can skip some tests that aren't relevant to that change set. Run less tests, it'll go faster. Or a simple technique most often desired by my industrial collaborators, just simply parallelization, where we say the cloud is cheap, just take my tests, parallelize them in the cloud, run them faster. So where do dependencies come into this problem, this picture? Let's consider dependencies between test cases. So we might typically assume that tests can be run in any order with the same result. However, to get that effect, we're probably going to be relying on developers to completely reset the system under test between these tests to make sure that there's no dependency. The problem with this is who is testing these tests and making sure that the setup and teardown is correct? We might have assumptions that aren't holding. And this can be really dangerous. If we're wrong, we might have false negatives when we see tests that pass that should fail, which are super dangerous, or false positives where we have tests that fail that should pass. So with this idea of test dependencies in mind, let's look at how this is going to interplay with these test acceleration techniques. So all of these test acceleration techniques rely on what is called the controlled regression testing assumption, which is to say we're going to be making some changes about how we run the tests. So as we run multiple successive versions of the test, the only thing that can change should be changes in the code and changes in the test. That should be the only thing that should impact the outcome of the test. Any sort of external influences should be kept constant. So for these popular test acceleration techniques, we and others, including some in Mike's group, have observed that they're often not sound in practice because these environmental assumptions that there's no external factors changing can't be enforced. So note that some of these factors might occur whether we're doing this test selection or test parallelization or minimization anyway, right? Maybe there's just some non-determinism in our tests. But every single one of these approaches involves removing or reordering tests, which makes them especially prone to this problem of test dependencies. So if we can't respect these dependencies, then these techniques make the test results unreliable and unsound. So what can we do with these dependencies? There are basically two high-level approaches. The first is say, let's isolate these tests. Let's prevent any dependencies from ever occurring, and then we can run them however we want because there will be no dependencies that can occur. And the other might be to say, let's really precisely detect what all of those dependencies are so that then we can do some test acceleration keeping in mind what those dependencies are. So let's consider the first solution, isolating test cases. So I surveyed a number of open source Java projects, finding that from this study, about 40% of the projects were doing some isolation of their test cases. And in principle, this is nice because it allows for some perfect test selection or parallelization. I can say I want to just run a single test and run it and not be concerned about some dependency it had on a prior test.
When you say they isolate, do you mean they have some kind of setup or teardown? Or do you mean
I mean something beyond having a setup and teardown. So in this case, it turns out that what these test suites were doing were isolating their tests by running every test in its own process.
Okay.
So we basically observed this process where for an entire test suite that might have, say, 1,000 tests, for every single test, we'd start a new process, a new JVM, we'd run the test, and we'd stop it. But yes?
And they don't modify the file system or set environment variables or anything like that?
So in this case, the isolation that they were doing was just this. They weren't being concerned with file system stuff, and they weren't being concerned with environmental variables. But yeah, that's an additional risk of how these tests might be becoming dependent. So basically, we found that what these test suites were doing was starting a new JVM for every test. And we said, well, if we're going to be accelerating things, maybe we should look at this. Because just this process of starting a new JVM is not free. In fact, on average in our evaluation, it took about 1.5 seconds to start a new JVM for these processes. And the overhead of this compared to testing overall is going to vary with how fast our tests are, right? Because we're starting a new JVM for every single test. So with unit tests as fast as 3 to 5 milliseconds, we were seeing this fairly constant 1.5 second JVM startup time. It's like several orders of magnitude of slowdown just from starting a new process for every test. So how can we do this better? So to create a faster mechanism for getting the same sort of isolation, just thinking again about this in-memory process isolation, just to kind of be a drop-in replacement for what was happening previously. So let's consider how tests might become dependent on each other. So hopefully don't need to refresh this one that much, that Java is memory managed and object-oriented. So we think usually in terms of object graphs, right? So we have some test runner, and we make it, and our test runner object can make a whole bunch of tests. And those tests can make some objects. And as long as the test runner isn't sharing references between tests, there should be no crosstalk between the tests, except for global variables, which would be our static fields in Java. And these static fields are owned by these classes, not by instances, so we can just reference them anywhere. So these are our leakage points. These are basically like the heap roots that we need to protect access to identify that maybe two tests will be becoming dependent on each other. So let's look at a simple execution of two tests, think about how these side effects might occur, and what we can do more efficiently to prevent these side effects. So I have two tests, test 1 and test 2. Test 1 starts, it writes some field of one class. It reads some other global field. And now test 2 comes, and test 2 tries to read some global field that was previously written by test 1. So this could be some leakage. This could be some side effect occurring, causing a dependency. So intuitively, what we want to do is at this moment identify this read, intercept it, before allowing it to occur, reset those global fields back to exactly what they would be initially if test 1 hadn't run at all, and then allow the read to occur. So the insight here is that these other global fields, all of these other classes, had no possible conflict, so there was nothing we had to do with them. And we definitely don't need to reinitialize the entire JVM just to get this level of in-memory isolation between tests in the process. So I implemented this technique, which we call unit test virtualization for Java, creating VMVM or VMVM, named for its mechanism of creating a VM-like container within the JVM. So it isolates these in-memory side effects, and it provides identical semantics to restarting the JVM. It integrates very easily with build tools like Ant Maven and test running tools like JUnit. And it's implemented completely with application bytecode instrumentation, which means that it doesn't require any changes to the JVM. It doesn't require any access to source code. You can just basically drop it in instead of saying to Ant or Maven, run each test in its own process. Say, run them all in the same one, but use VMVM to make it faster.
What?
Yeah.
Maybe I'm asking slightly too early, but
Yeah.
all these Java language lawyer questions.
Yeah.
You probably know them better
Yeah,
than me.
sure.
But like for one, class loading, static initializers.
Yeah.
They only get to run once, stuff like that. Okay.
So exactly what we do is we make it look like a class is uninitialized the first time it's accessed per test. So what Dan's suggesting here is, there's kind of this way that the JVM initializes a class when it's first executed. Basically what happens is there's just some special method on every class. It's called CLInit. That is called when the class is loaded, and this causes it to be initialized. So our high-level idea is that there's already this mechanism for initializing something to a clean state. So all that we need to do is coerce this thing to get called. And we do this entirely within the scope of Java bytecode by adding guards around any place that might cause some class to be initialized. We have a check that says, do I need to reinitialize this? And if so, call the reinitializer. And by using these semantics, rather than just like checkpointing an empty state of a JVM, but instead completely re-executing these static initializers, we can guarantee that any sort of dynamic behavior that occurs in these class initializers occurs the same way that it would normally. We can also cover like reflection and stuff like that to hide the fact that we exist and to intercept those kinds of cases too. So we evaluated the relative speedup that VMVM would afford compared to this traditional fork run every test in its own process. So I show here the relative speedup afforded by VMVM. So bigger is better. On average, we saw about a 62% reduction in testing time using VMVM. So looking into these numbers a little more, we found that the speedup was really directly related to the number of tests and the speed of each test, which is kind of intuitive if we think about it, because so in cases like UPM here, there were like thousands of really, really, really fast running tests. These were like 3 to 5 millisecond tests. So testing was really being dominated by this time of starting a new process, so we really helped a lot. In cases like the bristlecone subject, where we had no speedup whatsoever, this application had maybe 10 tests that each took maybe 40 seconds to a minute each to run. So there was really almost no time relative to the whole execution time spent in between tests. So there was less acceleration. So I also consider the relative overhead of doing this relatively fast isolation compared to not isolating anything, just run everything in the same process. And I found an average overhead of about 34%. And it's kind of an interesting distribution here, too, where we see for some test suites, it was very low overhead. And in some cases, like the closure compiler here, it's like way, way, way slower, right? And from looking into this, what was interesting is that these tests were intentionally sharing state between their tests, because maybe there's some really long setup process that takes a long time to run. And the developers write some really quick reset method that they believe, and probably apparently does, bring the system back into a clean state, but without completing this whole setup thing every time. So regardless of how efficient I can make this process of doing the rollback, we still have to run this code every time that's defined as what happens when you start the test. So overall, we can see it's definitely still not free to isolate the tests. So this brings up a really interesting question. What happens if we have these really, really long running test suites, like these day-long running test suites, where they're not isolating the tests because they say, yeah, my test suite takes a day to run now, and if I was running each test in its own process, it would take 2 weeks, so we don't do that. So as I was working on technology transfer for VMVM, we came across several companies that had this problem. And they didn't want to pay this overhead of isolating their tests, but they wanted to do some test acceleration. Yes?
Sorry, before you go on, I'm sorry if I missed it. It seems like in terms of performance, if they're not purposely sharing state,
yeah.
And if they are, you have an opportunity, since you're guaranteed the result is independent,
yeah.
to permute the order you run it,
yes.
In order to cut down on the reinitialization. So have you looked at that?
So given that we're isolating them, we could run them in any order? Is what you're saying?
Or in parallel.
Yeah, absolutely. So you could definitely still benefit from some parallelization, but you'll still be paying some additional isolation costs. So it got really interesting. In some of the cases, the setup...
So let me back up. I may have presupposed a false thing in my question.
Sure.
Is the overhead from checking things or reinitializing?
Reinitializing things. Checking things is almost free.
It's almost free. And the reinitialization seems like it would depend on the order you run the test. You'd rather first run the tests that have smaller object graphs and touch less.
So we saw a lot of cases like this. I am testing an application that is deployed on a J2E server. And before I can test my little servlet and do this little thing, I have to start up Tomcat or Geronima or something that takes 8 seconds to do. And my test is 5 milliseconds. So it's a really long. I mean, if you have a ton of infinite computational power, it can get faster. But we actually experimented with running things in parallel with isolation, and it's really hard to break even in some other cases. Yeah. So we don't want to isolate things. So what can we do? Let's remember these 3 techniques that we want to run our tests faster, right? Remember, we had this problem, which was that they weren't really sound in these cases. We could have these unreliable builds because there are these dependencies and we don't know exactly what they are. So the answer in this case is we want to precisely identify what all of the dependencies are between the tests. And then once we have these dependency graphs, we have all kinds of algorithms that can work on these graphs and parallelize things safely. But the problem is that these dependencies can be hard to specify. So if we just said, we'll solve this by giving developers some annotations, and they can put these annotations on their tests and say that something has to run in a specific order. And I mean, we wouldn't be inventing that. Like, that already exists in JUnit and Maven, and generally, it's not really being used, and that's kind of why there's this problem, right? So we can't really arbitrarily isolate because it's going to add this overhead, and it's going to maybe make it harder to break even in some cases. So there had been a prior technique where we could definitely guarantee we're going to find all of the dependent tests, but it would require combinatorially running our tests. We find that if a test has a different outcome when run in a different order, then there we go. We have a witness of this dependency. But again, the problem with that, we're running our tests combinatorially. It's not necessarily going to be scalable, especially to these day-long tests with hundreds or thousands of tests. So the sort of dependencies that this prior approach is detecting are as called manifest dependencies. So the idea with this kind of dependency is that we have some data dependence between two tests, T1 and T2. When we don't respect it, we see the outcome of T2 changed. So by this construction, all of these manifest dependencies that are causing these potential failures are themselves caused by simple data dependencies. Although not all data dependencies will necessarily cause a problem. Maybe there's some data dependence between two tests, but it doesn't have to be respected.
Data dependencies include things outside the JVM, like the file system?
Yeah. So rather than search for manifest dependencies, which to identify, we're going to have to actually try the test to see that there's a witness that it's going to cause a failure. Our insight was to search instead just for simple read over write and write over read dependencies. So let's consider this example. We have 4 tests. As they run, we monitor access to shared data. In this case, let's assume there's only one thing that can be possibly shared between these tests. And then we can infer that test 1 has to run before test 2 and 3, and test 4 must run after test 2 and 3. And if we follow that order, we know that there can't be any sort of manifest issue when we run it, because it's going to respect the data dependencies. It might be over-restrictive, right? Like maybe this data dependence doesn't actually flow into anything. It's just something that's being read. Maybe it's a log file. Yeah.
It seems like you're depending on the fact that these tests are run in the same order every time. How do you know that? So for instance, imagine that tests 2 and 3 are expecting to see B, but they accidentally just now saw value A.
Sure.
But because we ran them in the wrong order, like test 2 and 3 don't fail.
So great point. The assumption is that we have some baseline order that we expect the test to run in normally. Okay. So in a lot of cases, this is you run your tests are grouped by test classes and test methods. The test classes are grouped by file system order, so vaguely alphabetical, although if you're familiar, it's not quite, right? And then your test methods are run in usually a random order, although there's a funny story behind that too. They weren't always random, and that caused a lot of headaches. So kind of our key insight here is that what if we're just give up on this idea of being super precise in finding these dependencies? Let's just have some tractable system that can find relatively quickly all of these data dependencies between tests. And if I report some that are not truly manifest dependencies that I don't have to respect, maybe the outcome is still going to be usable for our clients because they'll be able to do some sort of acceleration.
So this is an insight for your particular problems.
Yes.
Right?
Correct.
So there might be problems where this isn't the case.
Absolutely.
This is the case for your particular problem.
So for instance, we're only going to tell you what the dependencies are with regard to a known correct set of orderings, right?
Well, it's also the case that this is intended to be used by an automated tool, not to be given shown to a human.
So it could be, and that's not something that we really evaluated very well, but we can provide a complete list of like all of the data dependencies that occurred, sure. Yeah. But then it's up to the human to kind of sort through those and figure out which ones matter or not. So we built this tool, ElectricTest, that detects data dependencies in Java. It tracks the in-memory dependencies within the process using a JVMTI Java tooling interface plugin. And it uses this IO trace agent to track file and network dependencies as well. It's implemented entirely within the off-the-shelf Oracle or OpenJDK JVM, up against the bytecode spec and the JVMTI spec. So there are no specialized anythings required. And so it can capture complete stack traces when these dependencies occur to support debugging. So this way, maybe we could tell developers, hey, these tests had this data dependency. It was on this field called log. Maybe now you'll look at that and say, I don't care. We could say it's on some other field that you do care. And most interestingly for our problem, though, we also generate these dependency trees to enable sound test acceleration. So the key technical contribution from the implementation side of ElectricTest is its technique for detecting these in-memory data dependencies at a very fine granularity. So ElectricTest tracks the reachability of all variables on the heap from the different heap roots, which in our purposes are static fields. After each test, in this case the first one, we force a GC, a garbage collection, to ensure that anything that's left are things that might be reachable later on. And then ElectricTest traverses the heap to map variables back to the static field or fields that point to them. And in this process, ElectricTest will be annotating each previously unannotated new variable with a generational counter to indicate that it was written in the most recent test, in this case, test 1. And by knowing which heap root or roots point back down to each variable, it's going to make debugging and analysis of these dependencies much simpler later on, although it's not strictly necessary for saying which tests are dependent on which. So then when a future test is running, in this case, let's say test 2, ElectricTest continues to monitor all accesses to the heap. Maybe we see some variables are written over, and we update the generational counter saying this was written now. But now if we see that some variable is read that was written in a previous test, we know this is a data dependency, and we can report this at this really precise object level, reporting no false positives for these in-memory data dependencies. So that's the in-memory picture. So we also capture external dependencies too, say on the network or file system. So ElectricTest uses Java's built-in IO trace mechanism to intercept all of these accesses and log them. For ElectricTest, in this default configuration, we consider that any two tests that access the same network host or that access the same file in any way are data dependent. So this is perhaps an over-approximation. It's also not necessarily sound. Maybe you have two network hosts that are different and they're actually colluding and sharing data back and forth between them. But we found this to be a sufficient approximation for our results. For finer-grained external dependencies, we could do a more detailed analysis, like at the file layer or on remote hosts. So with this dependency information, ElectricTest enables sound exploitation of existing test acceleration techniques. The simplest thing that we can do is, say, enable safe test parallelization by automatically generating a schedule that respects these known dependencies. Similarly, this dependency information could be used to enable sound test selection or prioritization. For any test that's selected to be executed, ElectricTest would provide the dependencies for that test, ensuring that, hey, it's actually all of these tests that you have to run to guarantee that the outcome is going to be correct. So I show here a comparison, just as a straw man, between ElectricTest and doing this combinatorial manifest test dependency detection, just as a point that ElectricTest is faster. But to drill down and look specifically at its performance on its own on these tests, I found that it was fairly variable between being really, really fast and, in some cases, almost prohibitively slow to consider running on anything of a regular basis. So looking into this, this was really interesting. It was almost an inverse of the properties of how VMVM worked, in that in test suites like Time that have a lot of really, really fast tests, ElectricTest was dying basically in performance because we have to pause between every single test, do this garbage collection, traverse the heap, check all these things, when the tests themselves are relatively fast. One possible solution for those cases might be to group tests together into buckets, maybe, and consider parallelizing individual buckets. And instead of saying that you can have all of the tests in any order, maybe I'll have groups of 50 tests and put those tests in different orders. So I also considered perhaps a more important question, which is, we know that these data dependencies might be over-constraining things. I might be reporting so many dependencies that don't actually matter that now we can't really get any speed up because we've got too many dependencies. So I simulated the parallelization of these 10 test suites across the 32-core hypothetical machine. So in the unsafe configuration shown in red, a hypothetical maximum, I ignored all of the dependencies that we detected and just distributed all of the tests in a round-robin fashion. In the safe configuration shown in blue, I simply enforced all of the dependencies, generating a schedule that was safe. So on average, the safe configuration allowed for roughly a 7x speedup, while the hypothetical maximum was still 19x. So overall, we found that there was definitely a reasonable amount of acceleration possible, even with the potentially over-approximation of the number of dependencies reported by ElectricTest. So before I switch gears to a more general dependency thing, I just want to recap the first half of the talk, where I described how testing dominates build times and how slow tests can be a problem for developers. our first approach, VMVM, unit test virtualization, that can cut this high overhead that developers pay for isolation, and the complementary approach, ElectricTest, to precisely identify these data dependencies between tests. But now we want to zoom back out and return to this original high-level idea of data dependencies. Yes. Yes.
So you said you looked at the hypothetical speedup.
Yeah.
Do you have any? Did you do anything to actually look at actual speedup and running it on maybe not a 32 core machine, but having a core machine? Or anything like that?
Yeah. So for a subset of them, we did that. The limitations in doing that were largely, technical, like unrelated to the system. We had to build our own JUnit distributed parallel runner that was kind of like its own implementation mess. They generally mirrored this though. Yeah.
So on the dependencies,
yeah.
Automatic is good.
Yeah.
Especially because the conventional wisdom to test writers is you should be independent.
Sure.
But they're not,
yeah.
and they probably know they're not.
Yeah.
Has anyone looked at letting them specify the DAG and writing a tool that would check it?
I am not that familiar with that one. I know that there are some extensions to JUnit where you can specify some constraints on run order, though. Yeah. So the second set of projects, Phosphor and Pebbles, are related more to just general data dependency and how it might be related to testing. So Phosphor is a tool for performing a general sort of dynamic data flow analysis, taint tracking. So taint tracking allows us to treat an application as a black box and observe relationships between inputs and outputs through data flow. So with taint tracking, maybe we can mark or taint some inputs and then have this black box analysis running on our app, and then we can see outputs that are derived from this input that was marked. So there are a ton of really interesting applications of taint tracking, especially in software engineering. But the problem where I step in is that there's not really any existing tool for the JVM that works off the shelf on a regular JVM and does this efficiently. So to do these kinds of analyses, the requirements that I set out is that we need something that's performant. It's something that we could maybe hopefully one day see deploying in the field. It's something that's portable. It's something that doesn't require specialized JVMs. Maybe one solution to this is we hack up OpenJDK and then have our special version, but that's not a great story either because then there's a new version of OpenJDK and we need to come up with a new hack. And it also needs to be sound and precise. So there certainly have been many low-level approaches before our work that work outside of a language runtime, like at the operating system level or by doing binary instrumentation. But the problem here is that you lose all of this rich information that's available inside of the language runtime. So my system, Phosphor, fills this gap by leveraging the benefits of these prior systems that required modifying your language interpreter, your runtime. But we do it without any source code and without any interpreter modifications. And we do this by instrumenting all bytecode that runs in the JVM. Like every single instruction that runs in the JVM, we own and change. And effectively, it's going to be adding a new variable for every variable, as well as propagation logic. So these extra variables will hold this information about how tainted or marked something is, and then we have some logic to propagate those relations. So really, the key technical contribution from Phosphor was a few insights in how we can efficiently store this metadata for every single variable without modifying the JVM. So at a high level, our solution is to add a variable for every value. So if we have objects of some class, maybe this is easy. We could add some new variable that stores our taint. If we have some local variables, maybe we can add some new variable in the same scope. We'll just make a new local variable. So it starts to get a little bit more complicated, though. Let's see how this might work out in practice. So I've got a few variables here, and I call some method. So again, for these local variables, we'll add some other variable. When we combine things, maybe we will just combine their tags. In this default mode, Phosphor uses integer tags, and it bitwise ORs them to combine them. But it can support any kind of object, and you can have a callback and combine them however you want. So now it's going to start getting a little more complicated because we have to call a method and pass some primitives to it. So we're going to change its method descriptor to also take an extra parameter and pass back some return value that is a union type of the value and the tag. And it starts to get a little more complicated, right? So it turns out if you want to keep extending this and just say that's what we're doing, then you end up with this. It turns out it's pretty easy to segfault the JVM, which was disappointing. So what are the complications? First, we have to deal with primitives on the stack. So JVM is stack-based. We said we'd add a variable for every variable. How do we handle the stack thing? Second is, it turns out there are some classes that you can't add a field to, because JVM has hard-coded offsets to fields and constant pool entries in the class file, so you just can't change them. The next is what the heck we do with arrays when we have primitive values, because we said we'd add a variable for every variable, but what do we do when we have an array that has a bunch of primitives in it and we need to have an extra variable for those? And also, if you're that familiar with this story, it turns out you have multi-dimensional arrays, then these are kind of how you handle that when you upcast and you no longer say this is an int array, but it's an object, and you can downcast, and where does that all go? And lastly, the usual complication of native methods. So we have code that we don't own, and what do we do? So to efficiently handle the stack story, Phosphor doubles the entire stack effectively by changing every stack operator. So here's an example of some code snippet and maybe what the instrument version of the code snippet looks at source code, although remember, we're not doing source manipulation here. So what the bytecode might look like that's generated from this. So the first instruction might be iload1, which would load the first argument onto the stack. And then iload2 to load the second argument onto the stack. And Phosphor will be loading onto the stack the first argument and also its tag, and the second argument and also its tag. And then the next instruction might be to add those two operands on the stack. And Phosphor generates some more complicated stack operators here that will reorder the stack to put the two things we're adding at the top and the two tags underneath it, and then add them, and then do this bitwise OR between the tags. And then we would be storing that result into some local variable. And then again, Phosphor would store that into the local variable and also store its tag into the local variable. So the result of this approach, where we're making the stack bigger, is going to be that these methods might get long, like there might be a lot of extra instructions embedded. But it avoids the need to have some other tracking that's happening somewhere else, something that can't be inline, something that can't be optimized for tracking the stack stuff. So the other big question is what we do with these classes.
Do you run into size limits on methods?
Yes. So it turns out that JVM has a limit of how large a method can be. It's 32 or 64K, I guess?
64, I think.
64. So if we keep doing this, we're going to end up with some big methods. So there were several cases where we hit this. These were generally cases where you're loading really big constant arrays into an array. Our solution to this was basically to install a simple optimization. So when you have a new array and you're storing a constant into it, for the kind of taint propagation that Phosphor is doing, it would always be storing an empty tag into an array of empty things, so it just doesn't store it. And that solves the problem. In principle, though, you could hit this wall on anything.
Right. I've seen this for real methods, too.
Oh.
So for,
sure.
For generated code from lexers or they generate just enormous table switch statements, and you can still hit up at that level.
In principle, you should be able to split the method. In practice, someone else can implement that.
Okay.
Yeah. I mean, another fix is maybe we recognize that we're going to hit the wall, and then we go back and we, instead for that method, inline less and have more calls somewhere else. Yeah.
Just out of curiosity, since John, this is a bit off topic, so we should do it quickly, but since John said he hit this in lexer tables, I wonder if lexers themselves have implemented switching, although maybe splitting, although perhaps special case to their domain.
So I've seen a lot of generated code that it is realizing this is going to be a problem. I forget what this is in. It's in some Apache project, but they have a whole bunch of files that are this, where it's like AA0, AA01, AA02, that each one is like just shy of the bytecode limit, right? And they realized that they were going to go like 8 times it, right? And they already cut it. So maybe you could change that in the generator to make it even smaller, but I don't know. So what do we do with these non-modifiable classes? We can't be adding this field to them. And what do we do with these arrays? What do we do with them? So one candidate approach could be use like a weak hash map, where we have every object and use it as a key, and then its value is going to be what its tag should be. And the problem is that this is going to degrade in performance. Like we wanted something that's going to be close to like usable in deployment. We're going to need to access this globally locked hash map for every single operation you're doing that requires a tag. So that's not a great story. So Phosphor basically sees a whole lot of special cases here. So in the general case, Phosphor is going to add this extra tag, extra field to classes. And if it can't, then it's going to use this hash map thing. And when we have primitive arrays, we give them a shadow array, and then we track those through upcasting. And as you move when we move arrays around, we also move the shadow arrays around. And this solves through multidimensional arrays too. And if someone wants to go into details, I've got plenty on that, but I'm going to skip through it lest we glaze over. So the last big question mark is native code, right? So we can't instrument everything. It's possible to implement functions in like C or C++. We're only doing bytecode manipulation. What do we do with that? So two problems. One, make it not segfault, and two, have some sort of reasonable propagation here. So here's an example of a call to native method, hash code. It's native. We can't change it. So the problem here is going to be that our caller that we're modifying is going to expect some function that's going to return this tainted int, this union type of the int plus its tag. And we can't change that method, though. So our solution is that we use wrappers. We rename every single method and leave this wrapper behind and always call the wrapper. So these wrappers have some extra part of their name. And they're going to be the glue, because they're going to know they're in the same class right next to the method definition that does it wrong, and it's going to have some glue in the middle. And these work both ways. So we can maybe have native code that's going to try to call into Java code, and it's going to expect to use the old signature. Like maybe we have some method, some method. I've got some native code that's going to try to call this. And what does it do? So our fix is that we leave behind for every method a stub. And the stub is going to maybe do some sort of patching to ensure that there's the correct types at least. And then we can come back to talking about what we do about what these tags should be. So how we track taint tags through native code is really our main design limitation. So we use a heuristic where a return values tag becomes the combination of all parameters. So this was something that we found to be imperfect. It didn't necessarily cause any issues in our evaluation. We're not the first to use this kind of heuristic. Taintroid, which does taint tracking on Android, which is like very similar to JVM, same idea. You could get around this certainly by modeling these calls, which we could do too. So really the cool part was the performance evaluation of this tool, right? Like we wanted this to be really, really performant. So we did a huge evaluation in the paper on 2 suites of Macrobenchmarks across 4 different JVMs, a lot of suites of microbenchmarks. We looked at runtime, we looked at memory overhead, portability. For brevity here, let's just talk about Macrobenchmarks on one JVM, which was Hotspot. On average, we did pretty well with about a 46% overhead. So in comparison, like low-level OS binary instrumentation taint tracking tools like tens of X of overhead, and we are like less than 2X overhead. We looked a little closer into specific issues on some of these benchmarks. You see it's a little lopsided. Some of them are really fast and some of them are much slower. Found out that actually in many of these cases this was related to over-allocation of arrays. So we'd make these extra shadow arrays for individual arrays, and even if there was no sensitive data going into those arrays, we had to allocate this thing. So I don't have complete numbers on this, but so Phosphor is something published in 2014, still working on quite a bit. Roughly dropping numbers by about 50%. So like the LU search number is about 90%, and with these simple array optimizations, we come back down closer to about 40%. So I'm really excited. Yeah?
These numbers are with int tags or with the object tags?
These numbers are with int tags, and these, yes. So object tags are going to be a little longer, and with object tags, it's going to matter a lot more how much is tagged, because you're going to be allocating new objects, and you'll have lists of objects relating them together. And the really nice thing with the int tags is you can only have 31 distinct markers, but propagating them is really, really cheap. So Phosphor is available on an MIT license on GitHub. It's already been adopted by at least 3 independent research groups, including John and Dan, which is pretty cool. I've been actively maintaining it since its original publication. For instance, array handling has been much simplified and improved since the original version. We now let tags be anything besides just ints, which was what was in the OOPSLA paper. And we have some preliminary, although a little shaky handling for implicit flows. So zoom back out. We're talking about data dependencies. How can this help us with specifying complex and data-driven tests? So here's a very interesting application of data flow analysis for security testing. So let's make sure that when I delete something, I want to see that it's really gone. And let's just step back and think about what it really means to be deleting something. So like, it's easy to say, I want to delete a file and see if it's actually gone, right? But let's say I'm on Android now, and I'm using the email app, and I want to delete an email, and I want to see if it's gone from my device. So the first question we have to ask is, what is an email? Assuming no cloud, just our device, right? So in the built-in mail app, it looks something like this. We've got some SQLite database, and it's got a message table, a body table, and an attachment table. We'll have a row on each, maybe a few rows on attachment, maybe none. If we have attachment files and they've been downloaded from the server, we'll have some actual files on our disk too. And if we've ever viewed this email, there are going to be these web view cache things that is some internal result of what happens from it caching the HTML rendering. So the problem is, before we even answer this question of is our email deleted, we need to know every thing that makes up this email on the device. So to bridge this kind of semantic gap between what you or I might think as objects, like emails, and what data is being stored on our device, we created this notion of logical data objects, or LDOs, a unit of granularity for protection and auditing. And then we built a system that automatically recognizes these LDOs without application support. So example, in our email app, maybe we have accounts, which have mailboxes, which have messages, and have attachments. And we want to be able to allow our users to just say, this is something I'm interested in protecting, auditing, so forth, without having the app developer have to tell the user what that thing is. Like, we want to do this at a system level on modified apps. So our system Pebbles at the highest level plugs into 3 popular storage abstractions to reconstruct some latent structure, like from SQLite databases or XML stores or file system APIs. And then it builds this device-wide object graph. For each node is one of these atomic units of persistence, like a row in a database or an item in an XML file or a raw file that we know nothing about. And then we put edges on this graph, both by using the structure that we uncovered, but also by doing this dynamic data flow analysis. So we can see things that are related through data flow, and then that tells us with a pretty strong intuition that there's some connection between them. And then these LDOs, like the email, is the transitive closure of everything in that node. So to detect these objects without any application developer input, we leverage this insight that applications are getting much thinner and more functionalities are being implemented in these thicker operating systems, like on Android here. So while traditional system-level data analysis tools might sit just above the OS and the standard libraries, with Pebbles, we sit above this entire really thick and rich framework that all of these apps are using. So given this insight, basically the way that we implement Pebbles is by taking the regular Dalvik runtime and replacing it with Taint, which is a dynamic taint tracking system for Android. And then we modify all of the frameworks, like SQLite and XML Store and the file system API, to feed back in some information too. And then build this object manager that it's in connection with everything and provides the system-level service that tracks what the objects are, what their relationships are, and lets us build tools on top of it. So we can use this tool to develop all different, we can use this tool to discover all different kinds of LDOs or objects and all different kinds of applications. So like, for instance, I've hinted that the email app might have something like email attachment body and files. Maybe there are other emails too, and those things just have bodies. Some of them don't have files. There are these mailboxes that are related to these messages, and accounts are related to everything too. In apps like a to-do list application, we can find things like a to-do list, because maybe I have multiple lists and all of the items on that list. Or in a personal finance application, we find things like accounts and expenses and categories and all of the relationships between all of those. So once we have this information on LDOs, we can do a lot of cool stuff. For instance, we can do deletion auditing, where we allow a user to say, hey, I want to try to delete this email, check and see if it goes away. Now I deleted it. Did it go away? Or we can just simply provide high-level auditing and say, here are the things that were accessed. And rather than just saying a file was accessed, we can provide the user with more contextual information on what it was. Similarly, we can do distributed information flow control at the level of objects, or encryption and protection at the level of individual objects. So to study the accuracy of Pebbles, we evaluated on 50 popular Android applications by hand, where we manually identified 68 unique kinds of objects. And we identified most of them correctly, including many that aren't even shown on this slide. But to breeze through these, in the case of email, we found the accounts, folders, and messages. In the case of browsers, we found groups of history items and individual bookmarks. In the to-do list application, we found lists and items. In the personal finance application, we found the accounts, categories, and expenses. Overall, we found 60 of 68 of these unique objects correctly. So keep in mind we're doing this without any special requirements on the developers. We're not asking them to give us annotations. We're not asking them to code something in a specific way. We are just taking these apps off of the Android marketplace and running them. So we thought that was pretty cool to get that high of a measure of correctness. For 43 of the 50 applications, we found everything correctly in the application. And generally, in the cases where we were missing things or grouping too much together, this was because these apps were really heavily cloud-based. So remember, we're working only on the device here. So if you have some computation and relationships that are occurring outside of your device because it's mostly being processed remotely, we miss all of that. So presumably, we could extend such a system to also work on cloud-based services by owning those services too. Some cool findings. So we used the Bread Crumbs tool, and we found improper deletion in 18 of the 50 applications, including many that you may recognize. In many of the cases, an entire object wasn't being deleted. Sometimes this was a bug. In the case of the email app, it turns out that there had actually been a bug in that specific version of Android where, in some cases, they weren't deleting the attachment file from the disk. This was something that the Android developers found out pretty quickly because this was Android 2.3, so this was in the days where we had like 128 megabytes of storage on our phones. So if you didn't delete your attachment files, it was found really fast. But that was something of the kind of problem that Pebbles found. In other cases, we were just finding, for instance, that maybe objects weren't being deleted, but just hidden for applications that provide like an undelete functionality, like the Evernote to-do app. Or, I'm sorry, the Evernote note-taking app, right, where we're able to recover items. So yeah, we're finding that when you delete it, it's not really gone. So in terms of what's on my research horizon, the short term, I'm looking at a lot of Phosphor optimizations. In one case, we're really interested in trying to apply various hybrid static dynamic data flow analyses. Maybe the static analysis can be sound, but maybe imprecise. But it can inform our dynamic analysis. Hey, you don't need to do runtime checking in this area of the program. We already checked it. I'm also really, really excited in using Phosphor for other kinds of dynamic analyses, including, for instance, instead of tracking taint marks, use it to track path constraints on variables. In general, though, the broader interests that I have looking down the road involve tools and approaches to make it easier for developers to build reliable software, right? So for instance, dependency analysis for debugging. I'm really interested in exploring techniques to present runtime data dependency information to developers inside of a debugger. How can such information be used to improve debugging? Can we use this information to build profiles of apps to identify some that have similar behavior? Or what does it even mean for two code segments to behave the same but look different? I'm also really interested in looking at approaches towards helping developers understand crashes that occur in the field. So this is why one of the big driving forces behind my systems have been performance, getting towards a point where something is deployable in the field. How can we identify when an app is behaving in an atypical way? What information do we need to most effectively help developers reproduce that failure? How can we maybe automatically triage those failures? I'm particularly interested in applying Phosphor to build perhaps data flow profiles of applications, which can then maybe be matched at runtime and deployment and identify irregularities. So before concluding, I need to recognize the astounding mentors, students, and faculty that I've had the privilege of working with on this work and others at Columbia, UIC, UCLA, ElectricCloud, and Penn, plus the many, many undergrads and master students back at Columbia who contributed to my work and really helped me grow as a mentor. So to wrap up, in this talk, I've described how program dependency analysis can be an interesting and perhaps sometimes overlooked approach to considering software reliability. For instance, I described how testing dominates the overall time needed to build software often, which can make it hard to run these tests as often as developers might hope. I described my first insight towards accelerating testing, removing the need to execute individual test cases in their own process with this lightweight isolation mechanism. Then I looked at cases where test cases weren't being isolated, where it wasn't safe to use some off-the-shelf test acceleration technique, building ElectricTest, efficiently detecting these dependencies between tests. Finally, I described my dynamic taint tracking system, Phosphor, as well as our system for detecting these high-level logical data objects using taint tracking, Pebbles. Thank you.